Costas Bachas from École Normale, and he's going to talk about tension of holographic defects.
So let me start by thanking the organizers for having organized this marvelous workshop, if I may say so, with no defects and no boundaries. I have learned a lot from people from different communities, including, I would never think I would attend a category conference in my life. So yeah, it has been really a pleasure. I was here in September. I enjoyed it a lot, and I liked a lot also this week. I will talk to you about work which is mainly contained in these two papers. One is with my ex-student, Zhongwu Chen, who's now a postdoc in Beijing, and the second one is with Zhongwu and Lorenzo Bianchi. But it's motivated by several other papers with the people you see downstairs. I mean, that's how I came to ask the two questions that you will see here. And here's a very brief outline of what I will tell you about. The talk is basically, the hardcore is a defect CFT result. So I'll show to you a proof of some general relation, but the motivation comes from two classical problems. One is the famous problem of how do you define mass in general relativity. So this was famously solved by Arnovitt, Deser and Missner with the famous ADM mass. And the natural question to ask is, how do you extend this to extended objects and define what one would call the tension, or the brain tension, in general relativity? So this was one of the questions. And of course, since brains are dual to defects, this is a natural question to ask in the holographic context. The second classical question is even older. Sorry, no. I don't know how to use this properly. Yeah, it's even older. It's actually a problem that Dirac here tried to solve, and other famous people like Lorentz, Abram, and so on. Is there a consistent theory that describes Maxwell field interacting with classical charges? So this is a little bit in the spirit of Marco's propaganda. Marco is not around anymore, but can you, in a sense, go from defect conformal field theory to some consistent effective theory that describes the bulk and the boundary degrees of freedom? I will not really answer this for you, but I will make some remarks that may be useful. Okay, so introduction just to set the stage. So as I said, this is a talk about p-dimensional conformal defects in a d-dimensional CFT, and I will be most of the time leaving both P and D arbitrary. We will consider defects that are rotationally invariant, like in Julius' talk. So typically you break the conformal group to a smaller group, SO2, P, times the rotation group. And in particular, this is the Lorentzian case. Of course, there is also the Euclidean case where the groups are SO1, D plus 1. It breaks to SO1, P plus 1, always times the rotation group. Now, if the theory is supersymmetric, you also break at least half of the supersymmetries. And of course, I don't need to motivate in this audience why these problems are interesting. Let me simply say that, canonical examples include quantum dots in 2 dimensions, quantum wire junctions of the type we heard in previous talks, charged line operators, and so on and so forth. So in a sense, I will be talking about all of them simultaneously. Okay, now the data of DCFT, as we all know by now, includes the bulk spectrum and the 3-point couplings. And then there's also the defect spectrum. It's their 3-point couplings, so the 3-point couplings of the defect operators. And finally, the bulk defect OP coefficients, BIA. Now, I will be focusing on these two universal bulk and defect fields, which are the energy momentum tensor in the bulk and the displacement operator on the defect, and we heard a lot about them throughout the meeting, so I won't go into too many details. Let me simply say that the locality of the theory imposes the existence of both of them. So I'm not going to talk about non-local CFTs. Local CFTs have a mu, and the defects have a displacement operator. And this obeys the well-known word identity of broken translation symmetry, namely T mu j in the transverse directions is not conserved of the defect. And this equation defines the displacement operator dj. It fixes also the scaling dimension of the displacement to be p plus 1. But importantly for me, it fixes also the normalization of the fields. So the normalization of these operators has physical meaning. Unlike most other operators, it's part of the conformal data. And in particular, the 2-point function of t is the central charge, the 1-point function of t and the 2-point function of the displacement define two parameters of the theory, which are a priori free parameters and which are part of the conformal data of the DCFT data. And to be more precise, if you think about the 1-point function of the energy momentum tensor, this was already shown earlier in this conference. It all depends on a single parameter. I chose the convention AT. There is some other convention which calls it age, and it's not exactly the same parameter. It controls both the energy density along the defect and the stress in the transverse directions. And likewise, the 2-point function of the displacement is controlled by something called the displacement norm. So these parameters will be the main actors in what I will be discussing. The displacement norm has to be positive by unitarity. AT has to be negative in my conventions for positivity of energy. So other than this, there are no constraints a priori on these parameters. Let me simply also mention that if you include local operators in the generic language of defects, so this is p equals to 0, then of course there is no displacement norm because you only have a point. And on the other hand, if you think about interfaces, codimension 1, there is no AT because the 1-point function of t mu nu vanishes. And you can see that both of these expressions vanish identically, actually. So in a sense, they are both defined only for dimension bigger than 0 and codimension bigger than 1. Now, what happens in holography, that's a well-known story, is that a defect is the imprint of the world volume of a corresponding brane on the boundary of anti-de Sitter. So if you have, say, a local operator, there is a particle in the bulk which is hitting the boundary at the position of the local operator. And if you have a string, then there is a line operator in the CFT, which is again the imprint of a world sheet on the boundary of anti-de Sitter. So I'm not going to go into details about this, but just saying that there is a holographic dictionary, whatever correlation function you write down in CFT, there is a gravitational path integral with Dirichlet boundary conditions that computes it in principle on gravity. Now, For local operators, or point-like defects in particular, there is, of course, this all-important quantity, the scaling dimension of the local operator. It is simply the same as AT up to some numerical factor. This is one of the first entries in the holographic dictionary. The scaling dimension is the invariant energy or mass in anti-de Sitter of the corresponding gravitational dual. So for extended effects, one expects by analogy that AT is related to some kind of invariant anti-de Sitter tension of the dual p-brane. Okay. Now, for line defects in 2 dimensions, and this is a problem, so this is a problem we had been looking at with Shira, Giuseppe, and our collaborators. So these are strings in ADS3. This is codimension 1, remember, and therefore AT is not defined. And in some series of papers, particularly this one, we related the tension, in this case, of the string to the energy reflected at the dual defect in the conformal field theory. And this, in 2 dimensions, this is a very nice quantity because it has been shown to be universal, particularly in an early very nice paper by Cuellar, Runkel, and Watts. And universality was actually shown later by Marco, Penedones, and Rosset. Now, in this particular case, R is actually basically the displacement norm over 4 times the central charge. So, you know, this paper established that tension is related to the displacement norm. So you may think that when both CD and AT are defined, there are 2 independent definitions of tension. Okay. So for generic P, there are 2 independent definitions of tension, and let us see more closely how to define them. So I'm coming to point 2. Is there any question up to here? So this is to set up the problem. So what's going on, first of all, in the well-known case of a point-like defect or a dual particle? Well, this is the one formula everyone learns in holography on page 1. Scaling dimension for a free field is related to the mass of the particle in the bulk through this equation, where d is the dimension of the bulk of the conformal theory. So this relates the scaling dimension to the mass of a putative free particle, and you may want to expand it in, for large mass, for a very massive particle. Delta is m0, and then there is a series of corrections. These corrections you can think of as being basically quantum corrections because the particle lives in a box. Anti-de Sitter is a box. So they are suppressed by powers of the Compton wavelength, 1 over m0, in units where the anti-de Sitter has unit radius. So I'm setting the radius of anti-de Sitter to 1. So these are all suppressed by powers of Compton wavelength over anti-de Sitter radius, like for a quantum particle in a box. Okay, now, of course, in general, the dual particle is not free. It has at least gravitational interactions, possibly other interactions, and therefore, even if m0 is much bigger than 1, we expect more corrections, in particular, classical gravitational screening corrections. So schematically, delta should have also corrections that are suppressed by the Schwarzschild radius, the would-be Schwarzschild radius, in units of the ADS radius, and this would go with powers of g Newton times m0. So there can, of course, be also other length scales controlling different corrections in full detailed holographic setups. But let me focus on this type of corrections here. You see, delta, the scaling dimension, doesn't care about any of this. It resums everything. So it's not only resumming the ADM mass corrections, the classical gravitational ones, it also resums the quantum corrections and anything else that may come in. So all corrections are resummed in delta, which is the invariant energy, contrary to M0, which is simply a parameter in an effective point-particle action. Okay. And the two are only equal in the limit where the particle is classical and it doesn't back-react. So this means that M0 must be much bigger than 1 and much smaller than the inverse Newton coupling. Okay, now this is for a point particle, so we can easily generalize this to an extended defect and define an invariant gravitational tension, an energy per unit volume, by essentially doing the same thing that you do with delta. You integrate the conserved dilatation current, but around a thin cylinder that follows the defect line on the boundary. So I define sigma gravitational by doing this integral of the dilatation current in the presence of the defect. And the only question that you may ask is what proportionality factor should you stick in here? Obviously, the right-hand side is proportional to AT, that's the 1-point function of T mu nu. And so the only unknown is this factor that I call gamma gravitational. Actually, very similar definition, although not formulated like this, has been proposed in the very early days of holography in a series of papers, particularly by Hammark and Obers, who discussed ADS tension, the tension in ADS of a brain. They didn't talk about it in DCFT language, but essentially it's equivalent. So this is the obvious extension of scaling dimension to brains, to defects.
Sorry, can I ask?
Yes, please.
The previous slide, this is computed in field theory or is it in gravity?
Sorry, should I, how do I go back? I'm not sure, yeah. So this one, so a priori, the formula here is a DCFT calculation, okay. Of course, if you can compute it in gravity, it should be the same. I will actually compute this coefficient in gravity in a minute, because that's where I know what to match to something.
You use ADS-70?
Yeah, so just hold on a minute, you'll see. But here I don't use for the moment gravity. I'm telling you that there is, analogously to delta, there is a notion of brain tension, which is simply AT times a coefficient, okay, and we have to find the coefficient. But I told you that there should be an independent way of defining tension. If you think about a string, the first thing you do is not measure the gravitational field of the string, you just measure the stiffness of the string. The stiffness of a violin string has to do with the 2-point function, of course, of the displacement, and therefore there should be an independent definition which is proportional to the displacement norm times another numerical coefficient, gamma in. And since, which again I haven't fixed. Now, since AT and CD are CFT data, that tells you immediately that both tensions are GR invariants, no dependence on parameterizations. So in a sense, I have done the ADM part of the work here. These are invariant mass tensions, and there are two of them. And they are generically, as I told you, independent because CD and AT are independent parameters. Now, how do you fix these numerical coefficients? Well, we argue as in the point particle case. Namely, we want that in the limit of a classical thin probe brain, no back reaction, classical, heavy enough to be classical, and thin, our definition should reduce to the bare tension, which is basically the parameter of a Nambu-Goto action for the dual brain. So, in this effective Lagrangian, Einstein plus Nambu-Goto for the brain, assuming that the bare tension is much bigger than 1, so no quantum fluctuations, and much smaller than 1 over g Newton, a tiny Schwarzschild radius, we should find our definitions to reduce to sigma 0. Okay. So this requires now a gravitational calculation, but it's enough to do the leading order calculation. You see, to calculate gamma gravity, so what I want to do is calculate now AT and CD in this theory as function of sigma 0, and I only need to do the leading order calculation and fix my coefficients so that the tensions I defined before, which were gamma in times sigma times AT, gamma GR times AT or gamma in times CD, should reduce to sigma 0. And I don't care about the corrections here, the leading result should do it, and this is of course a 1-point function of the graviton, and this is a 2-point function of the displacement operator. Now, so these are the two diagrams. They look pretty trivial, you know. You have to compute the 1-point function of the metric fluctuation and the 2-point function of the displacement. And I only want the leading order Witten diagrams. And even though it looks trivial, actually it's a relatively hard calculation. It took us a while to do it. And there is a very stupid reason. The reason is that the dual fields H Mn for gravity and delta x for displacement are not defined naturally in the same coordinate system. The reason is that the graviton, to use the standard dictionary, you should do it in the usual Poincaré coordinates, so you should perturb the Poincaré metric, but the brane fluctuations should be computed in a different coordinate system, xm, in which the residual symmetry is manifest. I think Julius mentioned the paper of John B. Zetlin and a third author, where they did this. I want to go into the details of this calculation. The new system is related like this to the Poincaré coordinates. And notice that this is a highly non-trivial change of coordinates. In particular, the natural ADS cutoffs in the two systems are related by a field-dependent reparametrization. So holographic renormalization in this problem, I believe, is an open problem, and I have talked to experts, and no one seems to know exactly what to do if you want to go beyond leading order. However, here we could get away cheaply. At leading order, things simplify, and actually the problem basically boils down to ensuring that the normalization of the ADS fields is correct. Remember, normalizations for us are crucial, so all we need to check are the normalizations of the fields. The cutoff, non-trivial cutoff dependence comes in at higher orders. And to do this, we use the word identities. Again, Philin and other speakers talked a lot about it. So there is one that relates the 2-point function t mu nu dj with the derivative of the 1-point function, and another one which relates again dt with the 2-point displacement norm. And these word identities remove all the ambiguities. They completely determine this 2-point function t mu nu dj in terms of this basic data CD and AT. This was done in this nice paper of Below et al, and Philin also mentioned it. So all we did was verify that the relevant Witten diagrams obey exactly these word identities, and this is sufficient to make sure that we have the correctly normalized fields. And after all, so if you want to look at the calculations, you should consult our paper. But after all the dust has settled, one arrives at the following expressions for the invariant tensions in terms of DCFT data. So you fix these coefficients by doing this calculation. Okay, now I'm coming to part 3. So the statement is that if the defect is superconformal, any amount of supersymmetry in any dimension and so on, these two tensions are identical, and this translates to this linear relation between CD and AT, which sounds awesome over here. It's very simple on the other side. Now, this has a history, this relation. It was first noticed by Maldacena and Ljupovic, who were studying radiation from a moving charge, and I'll come back to this at the end of my talk. It was proved by Bianchi, Lemos, and Maineri for line defects in 4 dimensions, and then Bianchi and Lemos, in a rather mystic way, managed to extrapolate from this and a couple of other examples the general formula, and actually it's exactly the formula that corresponds to equality of gravitational and inertial tension. That's how we called it. You may want to call it stiffness. Several other people have actually worked on directly or indirectly on checking this equation. I mean, my list here is incomplete, but this formula is generically true, and I will now tell you that you can prove it for all P and all D. So again, I'm going to skip details of the proof. You can stop me, but I will just outline how we did it. So our proof is inspired, of course, by these earlier works, and essentially it goes in 3 steps. First of all, we classified all superconformal defects. Actually, we only need the ones with minimal superconformal symmetry, because the rest then is automatically satisfied. So that's step 1. Step 2 is to express the supersymmetry relation, which looks rather mystic here. So we could express it as a condition of the correlator T mu dj, where it becomes very simple. And then when you express it like this, the first step is to use superconformal word identities to prove the relation. So these are the 3 steps. I'll go quickly over them. Step 1, well, essentially, again, several people have done part of the work. Here is the papers we based our analysis on, which we extended then. In particular, Agmon and Wang classified all line defects, superconformal line defects. We extended these works, and then Mike Duff told us that he had indeed, from a very different room, he was doing brain scans, he had also come to the same essentially classification, but they didn't publish it until much later. So the basic thing is that superconformal algebras are so rigid that the embeddings are very much constrained, and I won't go into details about this. Let me, for instance, tell you that n=1 superconformal theories in 3, 4, and 6 dimensions have no superconformal line defects. And this is something you can easily understand with just spin or gymnastics. The unbroken SUSYs must transform in an irreducible representation of the transverse rotation groups. This should be sitting in an E-rep of the Lorentz group, and the 2 spinors have the same dimension, real dimension, so you cannot break some supersymmetries. And anyway, you can go on like this, and here is the complete list.
What about 5 dimension?
What?
You claim the 3, 4, 6, but what about 5?
There are line diffs. So here is the full list where there are things. So that's the list. Okay, here are the superalgebras, the embeddings. So line defects in 5 with n=1 supersymmetry are there. In 4 with n=2. Also surface defects in 4, 5, and 6. P=3 defects in 5 and P=4 defects in 6. So that's the list. And this, as I say, these are the minimal supersymmetric, the CFTs. So both little n and capital N are minimal. There are, of course, extended supersymmetries, but our proof only uses one supersymmetry, so we don't need the extensions. Okay, again, allow me to skip. I mean, we can spend time on the technical details, but I want to get the main message across. So that was step one. The second step involves, as I said, this two-point correlator, TNUNU-DJ, which only depends on AT and CD. And the key point, again, is that if the supersymmetry relation between these two parameters holds, then the following is true about this two-point correlator. You take a complex transverse coordinate. Remember, codimension is at least 2. So take a z coordinate in the transverse space and look at this particular component of the correlator, TZZ, DZ. And the claim is that supersymmetry is equivalent, it goes both ways, to the fact that this is a total derivative, double derivative of this particular expression. This is valid for any P and D again, and for any number of supersymmetries, so it allows for a unified proof of the relation in all cases. The last step, and that's hard work, and Jean-Wu did most of it, is to prove now this relation by using superconformal word identities. Now, what you use here is that the Poincaré supercharges, they transform as spinor-spinor of the Lorentz and R symmetry groups, and we need the transformations of the TNUNU multiplet. This can be computed by writing down all possible terms and fixing coefficients so as to close the corresponding superalgebra. Again, many special cases have been worked out, particularly by these authors. Let me just give you a flavor of the proof by thinking about D equals 5, five-dimensional n equal 1 theory. In this case, the TNUNU is the top component of this multiplet. It has the R symmetry currents. It has here, it has the supersymmetry currents here. It has also a tensor field, a scalar, and a spinor. And basically, you write down the action of the supercharges on all these people here. It takes some work. You close the full superalgebra, which is F4, 2, and you find this result. And the same works for all cases. Now, what about the displacement multiplet? Well, this is a supermultiplet under only the preserved SUSYs. It's much simpler to write down, but it does depend here on the value of P. So schematically, and if I only keep the transverse rotation labels, I drop everything else, there is the displacement, which is a top component. There is a Golstino, which I learned here should be called the displacino. I like this word. And sometimes there is a scalar, but not always. This depends on P. Now, the proof needs only a single unbroken supercharge, one component. And there is a smart choice of defect orientation, gamma matrices, and so on, that simplifies the action. So you use a Q whose action on these particular operators that we want, TZZ and DZ, is very simple. So here is how it acts on TZZ and on two of its bosonic descendants. Crucially, you should choose Q so that the transformation of the displacino is exactly the displacement operator with no derivative of the lower component. So then, with this choice, then you write down supersymmetric word identities, Q acting on these three guys equals to 0. You use them to re-express in the end TZZ, DZ as a double derivative of this. And then this now has no more indices, very few indices, so it's completely fixed rigidly. Its kinematic structure is fixed. And this is enough to prove the identity that I showed to you, and all other cases work very similarly. That's the proof. Now, okay, I can just quickly tell you about some examples to give you some more concrete things to ponder. So the simplest example, it's a free theory actually, is n equal to Maxwell theory in 4 dimensions. This is a free theory. It has a gauge field and 2 scalar fields. And this is the usual energy momentum tensor of Maxwell, and the scalar fields have the conformal improvement, which is 1/6 times 2 derivatives on phi squared. And this theory has, of course, conformal line operators. These are simply charged particles coupling to a mu with charge E, and they can also couple to the scalars with a coupling G. This conformal line sources classical fields. These are trivial. That's the Coulomb field, and this is the analogous scalar field. So it's very easy to calculate using this formulae the two one-point function coefficients, AT for the scalar and AT for the vector, and they are written here. You can give these to your electrodynamics course students, and they would compute this. What about the displacement field? The displacement field, it was shown again at some point earlier, is a sum of the electric field and of the transverse gradient of the scalar field weighted to the corresponding charges. So it's again trivial to compute the 2-point function, and here are the displacement norms for the scalar and for the vector. And if you want the full theory, you should sum, of course, those two, and likewise sum the ATs. Now, the supersymmetry relation here for P equals 1 and D equals 4, line defects in 4 dimensions, you know, this numerical factor boils down to a -18, so CD is -18 AT. And you can easily check that this is not obeyed separately by the Maxwell theory or the scalar, but it is obeyed by the sum if and only if the two charges are equal up to a sign. And in this case, the defect is exactly half BPS. So that's the most simple example where you can check this statement. Slightly less obvious example is n equal 4 super Young-Mills and the line defect that Julius talked about in the previous talk. Now remember, this is dual to the fundamental strength in the bulk. In this case, well, this is proven. It was proven already. It was actually noticed in the paper of Maldacena and Lukovic that this holds. But in this case, we even have a complete expression for both coefficients at all n and at all Hopf couplings because of localization. So you can just ponder this expression, try to expand it out, and you see very clearly what I told you, namely, in the classical probe limit, the fundamental strength tension is square root Hopf coupling over 2 pi. When you look at the corrections from this formula, you find quantum corrections, Compton wavelength over radius of ADS. You find black hole-like corrections. So, you know, when you have a huge defect, it blows up, of course, into a black string. And then you find corrections like this. But in between, in this case, there are also corrections that scale with a smaller power of n, and this come in because there is in this theory also a D string whose Compton wavelength controls precisely these corrections. So in a sense, in this theory, there is never a black string regime of Einstein gravity. Before you arrive there, you are basically screened by the fact that it's a full string theory that has also D strings, or S duality.
Sorry, I think I missed some point. Can you
Yes.
clarify? These two tensions are equal is because of supersymmetry or is because of holography?
No, because of supersymmetry, they are not equal. So you know, if you take a non-supersymmetric string in ADS, it won't have this property. It's all because of supersymmetry. You know, again, the simplest example to convince you, just choose G different than E, and then they are totally independent parameters, okay? So this is only because of supersymmetry. Well, unless accidentally, you know, if you have many parameters, maybe accidentally it can happen, but it's only because of supersymmetry.
Is there something similar happening for the ABJM case?
Yeah, I didn't put it up there. Now, ABJM is codimension. Yeah, same story. I mean, yeah, I could have put it up there. I just wanted here to illustrate the fact that these corrections, you know, there could be new scales when you think about this expansion. But you know, if you were Arnold-Deser and Misner, you would basically worry only about those, right? About screening classical gravitational corrections. Of course, these are quantum corrections. The string has quantum fluctuations. And then there is this, which is basically in the theory, which is not in Einstein gravity, but it's in the full string theory, because here we have exact holographic views. The last example are Weil anomalies when P is even, 2 and 4. This, again, they were talked about in particular in Young's talk, also in Sergei's, but Sergei talked about codimension 1. I here want to have codimension 2 or more. Now, this involves intrinsic and extrinsic curvatures of the defects. So in the case of surface defects, this is the generic form. And the B-type anomaly coefficients have been shown to be related to AT and CD. Basically, the extrinsic curvature square controls the displacement norm, and the Weil tensor pullback is controlled by AT. There are some numerical coefficients in there. And there are many exact results, in particular for surface defects in 6 dimensions and in 4 dimensions, which are all consistent with the supersymmetry relation. Again, one can check it. For P equals to 4, much less is known. Actually, there is a real tour de force analysis by some of our organizers and some other people in the audience, which they managed to write down the full Weil anomaly. It has 19 even terms and 6 parity odd terms, and some extra terms when the transverse dimension is 2. So it's a whole mess, but the first 2 coefficients, I'm not detailing here the precise form, are again related to AT and to CD. And here the only results I know are in the classical probe limit, geometric results, like in a sense what we calculated. And in this case, as expected, you know, the tensions agree, and they agree with the Nambu-Goto tension sigma 0. So here it would be nice to have some corrections to this classical limit. Okay. Now, in the remaining 10 minutes, I want to talk to you about the final problem, a very old problem, and actually that's what led Ljukovic and Maldacena to this relation CD equals minus 18 AT for line defects in 4 dimensions. Well, what they were trying to do is reconcile 2 calculations of the energy radiated by an accelerating quark in N equal 4 super Young-Mills. Now you see, you can compute this in 2 ways. One is you have your particle and you give it a kick. So there is instantaneous acceleration here. It emits some radiation. And obviously, if you calculate the emitted radiation, you will find something related to the displacement 2-point function. So it's something proportional to CD. And that's how they computed the Bremsstrahlung in this paper. But then a different set of authors, you know, said, well, let's take a uniformly accelerating particle. This is conformal to a static one. So if we do a conformal map, we can measure the energy by calculating T mu nu, the 1-point function T mu nu, away from the defect, and this is a result proportional to AT. Well, the two disagree, and Maldacena and Ljukovic attributed the disagreement to the problem of separating radiation from the self-energy stored in the fields of the quark. In some sense, they are right. They also made the following guess. They said, well, this is n equal 4 super Young-Mills, so along with T mu nu, there is a scalar field in the same multiplet whose dimension is 2 less than the dimension of T mu nu. So why not use it to replace T mu nu by this modified energy momentum tensor, T tilde mu nu, with a coefficient psi? Now, of course, you may say, you know, this combination, this famous combination is such that it's still conserved, but of course it's not traceless anymore. But who cares? Why should the energy momentum tensor with which we measure radiation be a traceless one? Let's assume it's something else. And now, if you choose psi, they said, so as to remove the singular behavior of the transverse Tij at the line defect, the two calculations agree. So that was their remark. But why on earth should this work? You know, this is a nice guess, but the logic is somehow tilted. For instance, in Maxwell theory, the two calculations do agree without any modification of the energy momentum tensor, and even though T transverse is singular. So, you know, as usual, smart people can get to the right answer in a not so right way argument, but, and this is, I think, the case here. So, you know, the calculation is correct, as I will show to you, but for a slightly different reason. Now, to understand this more precisely, let us consider again our love correlator, TD, but now in a Lorentzian theory, and I want to look at a particular component, which is the energy flux in some transverse direction and the displacement. Now, remember, we know how to write down this in terms of AT and CD. Here is the full expression. It was derived in this paper. And the thing that is important to notice is that the most singular term on the light cone, when X and Y are light-like separated, is this last one. So this is the leading singularity on the light cone, and if you use retarded propagators and integrate by parts a la Linear-Wiechert and so on, you compute here a radiation flux which is proportional to the derivative of the acceleration. There is only one displacement, so you cannot get acceleration square. You would need two displacements, but you get a time derivative of the acceleration, which is proportional to this coefficient B1. Now, this is something that vanishes, of course, if you have periodic motion or if the particle accelerates and then stops accelerating after a while, but not for a uniformly accelerating charge. And this explains the disagreement of the two calculations. B1 being non-zero doesn't give you the same result if you do the 1-point function of T mu nu or the 2-point function of the displacement. Now, in Maxwell's theory, B1 happens to be 0. You can again check it with the formulae. So this flux is absent, and the calculations agree. But more generally, let's assume that the theory has a bulk scalar operator O with dimension d minus 2, which here is 2. We are in 4 dimensions, and with a non-vanishing 1-point function controlled by a coefficient AO. Again, one of the vanilla type word identities tells you that the 2-point function of O with the displacement is basically controlled by AO because it's a derivative of the 1-point function. So this BO here is 4AO over pi. Okay. So now, suppose we modify the energy momentum tensor as in Ljukovic-Maldacena by adding this combination. We can do one of two things. We can choose psi to remove this radiation term, which is proportional to A dot. Note that this violates the null energy condition because A dot has no sign, so the energy can go out and come in depending on the sign of A dot. So we can choose psi to remove this term, or we can choose psi to remove the stress in the fields, namely put Tij equals to 0 in the one-point function. And a priori, these two are two different choices. But the key point is that the two choices coincide if and only if the supersymmetry relation holds. So again, you can check this in the example easily in the example of n equal to SQED. In this case, the operator is phi square. And the good choice of psi is minus 1/6, which exactly cancels, removes the improvement term of the energy momentum tensor of the scalar. Now, this improvement term is known to violate the null energy condition because d plus squared phi squared has no definite sign. So if you precisely remove this term, as was pointed out by Fiol and Martinez-Montoya, you restore the neck. But supersymmetry tells us that the same exactly modification also removes all the stresses of the Maxwell field and the scalar field. So you know the pure Maxwell field has a Tij, which is Eij, is the electric field. So it's non-zero, but if you go to this supersymmetric setup and you modify, you basically remove the improvement of the scalar energy momentum tensor, Tij vanishes. So this is the basic statement, actually assuming a certain Lorentzian continuation of the Euclidean correlator. Here I still have a couple of subtle points that are not totally figured out, but I believe it's correct, allows you to extend this statement to arbitrary superconformal p-dimensional defects in any dimension, namely that there is always an improved energy momentum tensor which restores neck and kills the stress of the static fields near the defect. So, as I said, this is a time-honored question. Is there a consistent set of equations that describes the motion of a classical radiating charge? In particular, to make it more precise, is there a clean derivation of the famous Abram-Lorentz-Dirac force, which includes, so it includes the acceleration squared term, that's the loss of energy to radiation, but it has also a phenomenological short term, A dot mu, nothing to do with the A dot we found before a priori. This term is there, it accounts for reversible energy which is stored in the classical fields of the charge, and you can arrive to it in many ways, in particular by asking not to have runaway behavior in the Abram-Lorentz-Dirac force equation. So many famous people have thought of that, but there's no clean derivation of this. If you want to really derive this term by cutting off things carefully and renormalizing the mass of the particle, and I believe the reason is sort of clear. You cannot absorb a singular T mu in the mass of the particle unless the stress is zero. A point particle cannot absorb Tij, it doesn't have where to put it. It can absorb T00 in the mass, but it cannot absorb Tij. So it seems to me that this effort should have been doomed because of this simple remark. I'm not totally sure. Of course, you may say, well, I can always remove this by hand, but then it will show up, as I explained to you, in some neck-violating radiation. So anyway, I wish I could cleanly state to you that there is now an ab initio computation of this problem, but It's still work in progress. I was doing other things this year, and Zhongwu left to China, and Lorenzo is teaching a lot, so that's where we are. So I came to the end of this talk. Here is the takeaway. There are 3 points. Technically, the main point is that now there is a proof that for all superconformal defects, any supersymmetry, any dimensions, there is this linear relation. This translates to the equality of 2 invariant definitions of gravitational tension, very different from the usual BPS equations that relate tension to charge. Here we relate 2 tensions. Actually, this is not an inequality which is saturated by supersymmetry. Sigma GR can be bigger or smaller than sigma in. And of course, one may wonder, what does this imply for M theory and quantum gravity? And finally, as I said, SUSY guarantees that the same subtraction that restores the neck also removes the stress from static defects, and this may allow to revisit the famous Abraham-Lorentz-Dirac problem. That's the end. Thank you very much.
Questions? Well, I will ask you. Do we have any any comments about your what that this thing can imply in M theory of quantum gravity? Any?
Well, no, I won't, we are videoed, so I won't venture into anything. Obviously, the use of sigma in here is supposed to ring a bell, but it's not exactly the same thing, right? But of course, since we don't know how quantum gravity should look at the very, very short distances, my hope is that this tells us something. I mean, it's rather surprising that these very different ways of trying to define tension only agree with supersymmetry. And there are many hints that supersymmetry should be there at the deep UV for quantum gravity. So, no, I can't say over lunch, but I will say here.
Super minor, it's not about the beautiful aim of your beautiful last question. It's not about this, it's a minor point. You mentioned holographic renormalization problems in the setup. It was,
yes.
Yeah, I wanted to know, what does it, so you expect, everything seems to work and match, so
I think, many people are thinking about it. I had 2 weeks ago a long discussion with Yannis Papadimitriou, who wrote with Skenderis one of the early papers on this. And they were proposing some generic approach to this. But then upon, trying to go to details, I think that Yannis also said he's not sure, so he's thinking about it also now. Many people have thought about this. The problem is that it's easy to calculate defect correlation functions in one frame. It's easy to do bulk in another frame, but how do you do mixed correlators? Okay. And as I said, this change of coordinates, at least when you have a thin brane, involves the fields in the cutoff. I mean, it's very ugly. If you don't have a thin brane, it should be even worse, because it would be some kind of collective modes and so on.
But overcame, you didn't have to deal with this problem in the examples that you have seen? Or,
Well, because we only looked at the leading order diagram, so...
only for fluctuation, of course.
Yeah, we only did the leading order, and at the leading order you can get away cheaply. The two, I mean, if I can maybe show it to you why. Since you're asking, where I had this change of coordinates. Yeah, here it is. You see, this is the ugly one. YD is the depth direction. So you see that YD and XD are related by this non-trivial thing. Now, if you have quadratic transverse fluctuations of the brane, then it's very ugly. If you don't, the cutoffs are basically the same, but you still need to make sure that the normalization of the fields is correct. You know, no one tells you. So there is a subtle story of normal. We can talk about it later, but at this level, as I said, we could get away because we knew how to fix normalizations by checking the word identity, which completely fixes them. I don't know how to compute corrections, and it comes up in many other problems, you know.
If there are no more questions, let's thank the speaker again and go to lunch.